Our third video in chapter 19 is going to be a short one here, just to talk about the structures that these transition metals like to form. And take a look at the chart that we have here from your textbook, table 19.5, and think about this compared to the molecular geometries that we discussed in chapter 7 last semester. In chapter 7, we talked about electron pair geometries and molecular geometries. And you'll see some familiar terms on here, like trigonal planar, right, or octahedral. So some of that's old, but there's a lot of information on here that's new. Because we're talking about coordination compounds, there's a ton of different possibilities for the ways these things can form. Because not only can I have higher coordination numbers, right, 9 and up, but there's also different ways that these ligands can adapt to the transition metal in the middle. Okay, so you see, take coordination number of 4, for example, right? It can be either tetrahedral or square planar, depending on the oxidation state of the metal. We see the same thing with coordination number of 5 and 8. Okay, so the difficult thing, the challenging part, is how many different structures they can form. Okay? But the good news is that non-bonding electrons don't alter the structure like they did before when we had to worry about lone pairs, right, and how those can affect the geometry. Okay? The most common geometries for coordination compounds are tetrahedral, square planar, and octahedral. And octahedral is the best because with a coordination number of 6, that's the only geometry we see, regardless of the oxidation state. So I just mentioned what's already on this slide, right? Octahedral, tetrahedral, square planar, the three most common by far of all those possible geometries. And the coordination number, which we introduced in the previous video, dictates the geometry. Right? That's the first thing we look at, followed by the oxidation number of the center metal. Okay? Here I see 3 different coordination compounds. Okay, but because they all have a coordination number of 6, right? 6 aqua ligands over here, 3 ethylene diamines, but still a coordination number of 6 because it's bidentate. 6 chloro ligands over here, coordination number of 6. Even though they look all different, they're all octahedral about the center atom. Okay. But what we need to pay attention to, and what's old and new kind of wrapped together all in one here, is the idea of isomerism. Right? And remember the definition of an isomer from a long time ago. 2 chemical species that have the same chemical formula. Okay? But in the world of coordination compounds, we can get different molecules, different compounds, depending on where our ligands are. Thinking about these things in 3-dimensional space, because the location of those ligands can affect both physical properties and reactivity. And so we'll start by looking at a cobalt complex. And if we're thinking about a specific type of isomer, we've got a couple of them here. We're going to start with geometric isomers. Okay, those have the same atoms that are connected to the transition metal, same type of bonds, okay, but they're different with their orientation in space. Okay. Things are considered to be cis if the ligands are adjacent or next to one another. Okay. They're considered to be trans if they're across the molecule from one another. So looking at this complex next, look at the chloro ligands specifically. Here, the chloro ligands, right, are adjacent to one another. So that's the cis form. Over here, they're on opposite sides of the molecule. So they're trans. And a little hint that I like to give to do this is just draw a line between the two of them. If you can draw a straight line without going through the center metal, then they're cis, like that. But in order to draw a straight line, if you have to go through the center atom, then they're trans. Yep. And that's important because you see these have different colors. Things that are cis and trans have different properties even though they have the same formula. Right? Not only do they have different colors, they would have different dipoles, different solubilities, different attachment and reactivity in the body. etc. So that's number one, geometric isomers, cis and trans. How about number two? Okay. Optical isomers, more commonly called enantiomers. These are two molecules that again have the same chemical formula and the same type of bonds, but they're exact mirror images of one another. Okay. But to be even more specific than that, not only are they exact mirror images, but they're non-superimposable mirror images. So that's the definition of an enantiomer, a non-superimposable mirror image, because we'll have that here and in chapter 20. Okay. And these guys have pretty similar properties. They vary in how they react light, but they're really important in biology, okay? Because if we're thinking about like receptors with enzymes, only one of these things has the reaction that you want it to. So let's talk more about non-superimposable mirror images. Right? If I take two pens, right, they're mirror images of one another if I put a mirror between the two of them here. But I can put the pen right on top of the other one. They're an exact perfect match. Okay, so those are superimposable mirror images. That's not what we're talking about here. A non-superimposable mirror image, like your hands, okay, they're a mirror image to one another, right? But when I go to put them on top, the thumbs don't match up. Okay, so that is a non-superimposable mirror image. Okay? And just like you can't put your right glove on your left hand, right? They have different reactions. So here we see a generic metal complex, right, with 3 ethylene diamines. It's a non-superimposable mirror image because you see everything lines up with that mirror in the middle. But if I were to cut this and drag it and put it on top, it wouldn't match up. So it's a non-superimposable mirror image. What other types of isomers do we have? We have things that are known as linkage isomers. Okay. A linkage isomer is when I've got one ligand that can bind to the metal in the middle through 2 different atoms. Right? So like the thiocyanate ligand can bind through sulfur because it's got a lone pair on sulfur, or it can bind through nitrogen, who also has a lone pair. So effectively with those linkage isomers, you've got one ligand and it can bond this way or this way. 2 types of isomers. And lastly, coordination isomers, which is where you've got an anionic ligand, something that was in the inner coordination sphere, and you replace it with something that was outside the coordination sphere. So remember we talked about things being in the bracket, right? Everything that's inside the bracket here belongs to the coordination sphere. So I start with 6 chloroligands on cobalt and 1 bromide counterion. If I swap the bromide counterion, put it into the coordination sphere, and then pop a chlorine out, so effectively it's been replaced, that's called a coordination isomer. Okay? You just swap a partner. Somebody who was out gets in, somebody who was in gets kicked out. So to wrap those ideas together for this chapter, okay, pause the video and try and answer those 3 questions up top. Is this cis or trans? What's its name? And then try and draw the other isomer. Pause the video and give that a shot. The molecule as shown is trans, okay, whether you're considering the chlorine ligands or the amine ligands. Okay, they're trans to one another, because if I draw a line through there, I have to go through platinum in the middle. Naming the complex was covered in the last video, but it's good practice here. This would be called diamine dichloroplatinum. And then the tricky part is it's diamine dichloroplatinum 2. Okay, because this thing is neutral overall, there's no charge shown. The amine ligands are neutral, but the chlorines are both -1. So in order for that to be neutral overall, platinum has to have an oxidation number of 2. To put this together then in a perfect name, because we're now dealing with isomers, the full name of this would be trans diamine dichloroplatinum 2. And then to draw the other isomer, you just take any of these 2 and swap them. Okay, so if I swap the chlorine and the amine right here, then that would be cis diamine dichloroplatinum 2. So that wraps up isomerism and coordination spheres. We'll finish in the next video talking about crystal field theory.